Hello class, welcome to our third topic and fourth recorded lecture for Introduction to Material Science. This is crystal structures, and this will include, this topic is one topic, but it, like was the case of atomic structure and bonding, this will include two lectures because there's a whole lot of concepts and a whole lot of slides, so we're going to divide it into two lecture sessions. What we're going to do now is literally build on the concepts that we went over in chemical bonding in our last section, especially with respect to equilibrium, interatomic spacing, and bond energy, and literally start building up unit cells and crystals from atoms based on their spacing. So, although not all materials are crystalline, most of them are. And the ones that aren't have special properties and can kind of be thought of in terms of exceptions to the rule versus crystallographic material or crystalline materials, excuse me. So crystal structures are basically one way to answer the question of how do atoms pack together. So you can see we've got two different variations here. Over on the left you have what we would call a close packed structure. If you assume that those are atoms and you're looking down on a sectioned plane of atoms all packed together, and you can see the 3D version down below, you can see that you've got, for equally sized atoms, equal radius, over on the left, you've got literally as many atoms as you can pack around one as can be achieved. This is called close pack configuration or circle packing. Over on the right-hand side, although the atoms are still touching, and you probably have a nice strong bond, you've got a lot more empty space between them. You can see there's a lot more white, and it has a distinctly different appearance even in the 3D structure. These are both crystalline, but they have a very different crystal structure. So materials and packing. Crystalline materials. What's the definition? They're atoms that are packed in periodic 3D arrays. This is typical of metals. Almost all metals, almost all ceramics, provided they are not supercooled. Most polymers, I go beyond some and say most, although the fraction of polymers that are crystalline is much smaller than the fraction of metals that are crystalline. It isn't all polymers. So in ceramics you can get either one, and here's an example of silicon dioxide or silica in a crystalline arrangement. The silicon is surrounded typically by 4 oxygens, the silica tetrahedra, and although it is a hybrid orbital, covalent bond, it likes to pack in a fairly regular array, and this is an example of one of them. Silicates have tons of different phase forms that correspond to different types of crystals and arrangements. And this is just one of the many. If you're very interested in that type of thing, I would refer you to a mineralogy or a geology text. They definitely get into far more complex crystallography than we're going to touch on, although you'll begin to get a peek into their world when we do ceramic crystals. Non-crystalline materials are also known as amorphous, and that just means the atoms are not packed in periodic regular 3D arrays. And that inevitably means they have more space between atoms, and they're a higher energy structure. This usually occurs when you have something that's too complicated to arrange itself into its low energy equilibrium periodic 3D array in the time that it's given. So you tend to get this from things that we call sterically hindered or complex structures, and that's big and bulky, difficult to rotate and move, and with rapid cooling. And generally rapid cooling is the one that will give you an amorphous structure for something that, given the time, would have formed a crystal. And so here's a picture of a non-crystalline silicate, and it looks kind of the same in a way because you're looking kind of end-on at a lot of those silica tetrahedra, but you can see that compared to the picture above it, it's much more disordered. There aren't those beautiful little hexagonal regular shapes. Everything's just kind of covalently bonded any which way. So it's a higher energy structure. If you gave it enough temperature to overcome what we call activation energy, let it sit for a while, it would transform to its crystalline variation because it has lower energy. So why is that? Well, back to our equilibrium bond length. If you have random packing, got a bunch of atoms and they're just touching. They're a condensed solid. It's a solid. It's not a liquid we're looking at over there on the left. It's a solid, but it's certainly not crystalline. There's no regular periodic array going down there. Well, if you know that for a given bond, the atoms want to be exactly so far apart, no more, no less, well, this thing's everything from soup to nuts. And in fact, it's always going to go towards a little bit farther apart just because that energy well is not symmetric. So on the average, more of the atoms are going to be farther apart than they really want to be based on energy minimization of our interatomic spacing versus bond energy diagram, which you can see on the right. So if you look at that blue structure, the average real interatomic spacing is probably where that black dot is. That is not the bottom of the well, so on the average that structure has a lot more energy than it would like to have. It's not at equilibrium. Now if we let those atoms move and pack themselves such that they had an equilibrium spacing every single one, you'd have a minimum energy structure. Well, in order for everything to have the same interatomic spacing, you kind of have to have a periodic 3D array, which is a crystal. This is the drive for crystallization. It's the drive to get each and every atom into the bottom of that energy well. And in fact, the average spacing between atoms in a crystal, a characteristic of that periodic array, is going to truly be that interatomic spacing, that R0, which we can calculate if we have the A's and the M's, coefficients and exponents for our attractive and repulsive forces. So condensed materials, solids, will crystallize because it minimizes overall bond energy in the structure. Okay, ways to represent crystals. Everything doesn't crystallize exactly the same way, and that's again because of the differences in atomic shapes and sizes, atomic sizes and the bond shapes. Do we have a hybrid orbital with a covalent crystal? Do we have a metal crystal? Do we have an ionic crystal with widely different sizes of anions and cations? We're going to look at a bunch of each one. But in order to do so, we have to have some way of telling them apart. And there's two conventional ways of representing a crystal. One, you draw little circles or little spheres on the lattice points where you would have an atom, or in the case of a complex mineral, you might have a whole lot of atoms. And that just represents a nucleus or a group of atoms. It's representational. You can also fill in, at least in the case of single elements where everything's the same, what is a probable distribution of the full electron cloud. And that's kind of looking at that outer s orbital, which is a sphere, and it gives you this sort of the outer extent of where the atoms would interact. And it's also somewhat representational, symbolic, because we know electron clouds aren't all spherical, but it gives you an idea that you're not talking about hard little balls of a nucleus. You are talking about an electron probability distribution. So you'll see both, and quite often we'll use that filled in electron cloud model when we're trying to get an idea of planar packing and how many atoms on which lattice points are shared by which unit cell. And it helps us visualize a little bit better. Neither one is technically accurate if we're talking about electron probability distributions, but it's good enough. The unit cell. This is probably the most fundamental characteristic of any type of crystal structure. This is the fundamental unit. In polymers, the equivalent would be the repeat unit. This is basically a simplification of the packed atoms to, and here's the definition, the smallest repeating volume which contains the complete structure of the crystal. So it's the smallest unit you can go to that if you just repeated it endlessly in all three directions, you'd build the whole crystal. So here's an example of a unit cell for a face-centered cubic crystal. So you can see the whole crystal in grayed out form over on the left, and then the darker representation, just what is in the lines of the box. not the entire series of dark spheres, but only the atoms that are within the box. As you can see, we're whacking them. The face atoms, only half belong to that unit cell, and on the corners, only like an eighth. And that's really important when we start talking about atomic packing fraction, density, linear and planar packing fractions. It's very important to know how many atoms belong to a given crystal, because that's how we're going to add those things up very quantitatively. And then those properties will in turn tell us quite a bit about the materials we make out of these crystals. Believe it or not, these are really important for a lot of the material properties we design to. Okay, we're going to start and probably end with metals. We will touch on halide ceramics just a little bit, and it's fun to do some for exercises in unit cell manipulation, but as material scientists we are not going to get into the real complicated ceramic type crystals, and certainly polymer crystals we're just going to touch on qualitatively in the polymers section. Most materials that we use where we have to be concerned with crystallography are in fact metals. So it isn't too bad in terms of what we're going to need to know to do our jobs, and we can extend the ideas from metallic crystals to the more complex scenarios if we want to start designing ceramics or go into natural minerals. Metallic crystals tend to form the simplest of all crystal structures, cubic and the hexagonal close packed. And they may look somewhat complicated, but trust me, the others are worse. So we are lucky as material scientists that we get the simplest ones. Metal crystal structures tend to be densely packed. So those atoms are very, very close together. Reasons why. And remember, this is the downside to metals. That high density is expensive because we have to move all of that weight up into the air, or we have to accelerate it. You only have one element present. All the atomic radii are the same. That tends to give you the closest geometric packing. Not always the case, but tends to be true. More importantly, metallic bonding is omnidirectional. Call it non-directional. We don't have to observe any kind of set bond angles that we would get coming out of a hybridized orbital, nor are we limited by the need for charge balance like we would in an ionic crystal. Nearest neighbor distances are small. So that, of course, lowers bond energy. Electron clouds shield the cores from each other. Okay, so these are effective. Some of these are not unique. In the case of nearest neighbor distances being small and electron cloud shielding, those are in some respects characteristics of the metallic bond. But you don't have hybridized orbitals, and you don't have to worry about charge balance. So things can basically pack very closely with no other considerations other than achieving that minimum energy distance. Okay, getting into metallic type of crystal structures. There are basically four. Simple cubic, which is only one material that we know has it, at least as a single element, and then the big three, body and face-centered cubic, and hexagonal. So simple cubic structures, even though they're only represented by polonium and not very useful for an engineering sense, do give you a really simple way to visualize a crystal structure. It is literally a cubic system, meaning that every edge is the same length and they are all at 90 degrees to one another. There is an atom on every corner of the cube. An important characteristic of every crystal structure is what we call coordination number. If you're a chemist, you've seen this with hybridized orbitals and you've seen it with complexes. It has the same meaning here more or less, and that's the number of other atoms that surround any one atom. So if you look at the picture of the red atom, that's one of the atoms in a simple cubic structure. It's surrounded by 6. So it has a coordination number of 6, 1 surrounded by 6. Obviously, the lower the coordination number, the more void space there's going to be. The less of the volume of that unit cell is being taken up by atoms, and the more by space between them. Atomic packing factor. This is one of the first characteristics that we'll learn that relates to important properties, notably density. The atomic packing factor has a very specific definition, and that's the volume of atoms in the cell versus the volume of the unit cell itself. And here we assume that hard sphere shell electron cloud distribution, not just the tiny nucleus representation. So we're going to add up the volume of those spherical atoms that are contained only within the little box of the unit cell, and we're going to ratio it to the volume of the box. So the atomic packing factor for a simple cubic structure is 0.52, so only a little over 50% of the volume of the unit cell is actual atom. The rest is void. So these are pretty wide open crystals. And second characteristic that is very important is, especially as we get into deformation and movement of atoms within the crystal structure, are what's called close packed planes and directions. A close packed direction is a direction in the crystal where the atoms are touching. And you can see in a simple cubic, they're touching along the cube edges. A is literally the side dimension of the cube. It's also called the lattice parameter, or the lattice dimension. Getting a little bit more filled in here. Okay, so this gives us an idea of how we calculate atomic packing factor. So if our lattice parameter, or the edge length of our unit cell, is A, the volume of the unit cell is obviously A cubed, because it's a cube. To get the volume of atoms within the cube, we take the volume associated with any one atom, so that's 4/3 pi r cubed for the radius, where A is the lattice parameter. Since you've got two radii associated with that lattice parameter, the radius of any one atom is 1/2 of A, cube it. So the pink box gives you the volume per atom. And then you got to figure out, well, how many atoms are actually within that one unit cell? And here's where we have to partition and start cutting into the spheres. So each one of these atoms you can think of as being shared literally by 8 unit cells. So if you were to put 4 of these cubes all together to make a big flat parallelepiped, you would have a hemisphere on each of those spheres. So effectively then you'd have to have another parallelepiped to complete them. So there are 8 corners, 1/8 of an atom on each corner. There's literally 1 atom per unit cell. So that gives you the expression for atomic packing factor. You can calculate this also in terms of atomic radii rather than lattice parameter. It doesn't matter, because you can tell the A cubed, or if you started with atomic radius, r cubed would cancel out and you get a dimensional value. It's a volume ratio, atomic packing factor. So it's a very direct indication of how much empty space you have in your crystal. And that's related to all kinds of things that we'll use later on for material processing. Okay, second crystal structure, body-centered cubic. This represents most of your workhorse engineering metals, your first row transitionals, all of your ferrous alloys, and this shows chromium, tungsten, which are usually alloying elements or refractories. This is a workhorse crystal structure that you'll see again and again with structural materials or structural metals. So this looks a lot like simple cubic, except there's another atom right in the middle. And this picture shows red and white. That's just for clarity of representation. That white atom in the middle really is the same. It should be red, but it would be hard to see if it was red. So you have a cubic structure where you have 1 surrounded by 8. So obviously we have a coordination number of 8. Now if we want to start looking into atomic packing factor, now we have a little bit different situation, because the relationship between the atomic radius and the lattice parameter, which gives you the ratio between your atom size, volume, and your your lattice volume, your unit cell volume, you have to look down the body diagonal. As you can see with our filled model over kind of in the middle, our blue sliced up space filling unit cell. If you drew a line from corner to corner across the body diagonal, that would be a close packed direction. The atoms are all touching. So you go through 4 atomic radii when you traverse the body diagonal. So if you knew the length of the body diagonal, you would have an idea of the relationship between the atomic radius and the lattice parameter, because the lattice parameter, again, is going to give you the volume of the unit cell. So it turns out that ratio is higher, much higher than it was for a simple cubic. Your atomic packing factor for a body-centered cubic is 0.68, so quite a bit higher. And here you can see your body diagonal, atomic radii, and your lattice parameter being related there. If you just look at the cube edge, that's still your lattice parameter A, but it isn't really related to your atomic radius in anything that's very simple. But the body diagonal is really simple. 4R is equal to the body diagonal. So if we have the same kind of argument here, the number of atoms per unit cell this time is 2. We have the same as in simple cubic, where we have 1/8 on each corner, and then 8 corners, plus 1 whole one in the middle. So there's 2 atoms per unit cell for body-centered cubic. And now what we have to do is do a little bit of geometry and add up the length of the body diagonal in terms of the radius of the atom. So if we take that body diagonal and lay it out flat, obviously it's 4R, and then we just have to use Pythagorean theorem and say, okay, we have square root of A along one direction and A in the other, and so we get cube root 3A is the length of the body diagonal, and so we can relate that to the volume of atoms, solid, divided by, of course, A cubed, and that's where you get our 0.68. Most of your non-ferrous alloys, your non-iron based alloys, are face-centered cubic. You can see there's a big list here. Aluminum, copper, your 2 workhorse structural non-ferrous alloys, gold, a lot of platinum group metals, nickel, workhorse, corrosion-resistant alloy system base, silver, high conductivity. A lot of very useful materials are face-centered cubic. These are unique in that a face-centered cubic is a close packed structure. Hexagonal and face-centered cubic, and hexagonal close packed are the 2 densest or most volumetrically dense crystal structures that can be achieved with a single atom, and generally the densest that can be achieved, period. So these are also tend to correlate with higher density. Definitely you see lead there and platinum being dense. Those also have high atomic weight, but it's another contributing factor. The close packed configuration also affects their ability to dissolve other materials in interstitial positions between the atoms that are on the lattice points, because there isn't a lot of between, as we'll see when we show the atomic packing factor. Generally, it is, again, similar to simple cubic, except you've now got an additional atom on the face. So we've once again got corner atoms that are being shared by 8 unit cells, and then we have the face atoms being shared by 2. With body-centered cubic, we had corner atoms being shared by 8, and then 1 big one in the middle, or 1 equally sized one in the middle, but only being shared by 1. Now we have 6 faces, each face being shared by 2, so that gives us effectively 4 atoms per unit cell. And the coordination number is now 12, which is the maximum you can get. So 1 surrounded by 12. So you can imagine that this is going to be one contributor to the higher atomic packing factor. This is a little bit easier than body-centered cubic geometrically, because now our closed pack direction is across the face diagonal. So we have, again, 4R, where R is the atomic radius, related to root 2A, where A is the lattice parameter. So that allows us to calculate our volume fraction of atoms per volume of unit cell. And it ends up being 0.74. again, another big jump. And again, the calculations are the same as we did before, 4 atoms per unit cell, the root 2a being the atomic radius to lattice parameter relationship, and a cubed. Volume per unit cell is always going to be a cubed, so that's where we get our 0.74. And again, like the other two, you can calculate this on the basis of atomic radius instead of lattice parameter. It gives you the same thing. Our second close packed structure is not cubic. This is hexagonal close packed. And it looks like you can see it easiest with the nucleus representation over to the left, the small ball and stick kind of model. You start with 2 layers, and it's really 3 layers, all of the same thing, and they're simply offset a bit. But if you look at the GHEF on the top, you've got 1 atom surrounded by 6 in its closest packed planar circle packing configuration. And then you have that stacked such that layer J is similar, and each one of those is surrounded by as many as they can be in kind of the C direction there, the vertical direction. This is very equivalent to face-centered cubic. In fact, they are related in a very easily describable manner that we'll get to. So they both have coordination number of 12. Each atom is surrounded by 12. This one is a little bit different to envision, depending on how you look at the unit cell. There's 2 different variations on the unit cell, and it leads to a whole different system of crystallographic descriptor numbers called Miller indices. We won't be getting into that for the hexagonal system in this course. We'll only do it for cubic. So we'll just learn the general characteristics of hexagonal close packed without getting into real depth. But generally, you can look at the unit cell in terms of having 2 lattice parameters instead of 1. So in cubic, it was just A because it's a cube. It's symmetric in every direction. Here we have 2. So we have A, which is basically one side of the hexagon that you can see over on the bottom portion of our ball and stick model, and then the height of the triple layer model, which is the parameter C. So you have 2 lattice parameters. So the unit cell volume will be a function of both A and C. And you have 6 atoms per unit cell, 3 in the center that are fully within the cell, 2 on the face, which would be analogous to the faces of the face-centered cubics, and then you've got 12 corners, which are each shared by 6. So 6 atoms per unit cell, but the unit cell is not just, it's not A cubed. It's a function of both A and C here. And we will not calculate the atomic packing factor, but because we know it's close packed, we know it's 0.74. So we don't have to calculate it. One of the useful things we can get from atomic packing factor is theoretical density. So this is the densest we can get a material. No dislocations, no voids, no discontinuities, no grain boundaries, all of which are things that we'll learn about later. This is the highest you can get. So it would be the mass of the atoms in the unit cell divided by the total volume of the unit cell. Well, this is great. If we know how many atoms are in the unit cell, we know the mass per atom from atomic number, or excuse me, from atomic weight. This is easy. So in formula form, N would be the number of atoms per unit cell, A is the atomic weight, V is the volume of the unit cell. For a cubic system, that's A cubed, the lattice parameter cubed, and then Avogadro's number. So you can do that by mole as well if you want a little bit easier number. So here's the terms. So this gives you an idea of why metals are so dense. It's not just because they have a high atomic number, although many of them do. Some do, some don't. But they're packed pretty closely together. So if we come back to our formula, you can see A, the atomic weight, and is of the same order in the formula. It's linear with density, just like the ratio of N to Vc. So the number of atoms per unit cell has an equal effect on density as atomic weight. So metals tend to be pretty high on both. And that's where you get the spread. So if you look down at magnesium, I don't know what crystal structure it is. We can look that up, but it definitely has a lower atomic weight. If you look at platinum, it's a close packed configuration. I believe it's FCC, and it definitely has a high atomic weight. So that tells you an awful lot. As you move over to ceramics, you get a lower atomic weight from usually the oxide, the oxygen or halide component, and you're not always quite as tightly packed. Definitely not in a covalent bond. So as a recap, metals have close packing and often large atomic masses or atomic weights, and ceramics go the other way. Not all, but most. Polymers kind of are low on both. They tend to be organic, which means they're carbon, hydrogen, oxygen, maybe a little nitrogen. Even your heavier polymers, which tend to be silicones, even those are light compared to, say, platinum, for instance, and they have the lowest packing when they're crystalline, and when they're amorphous they're even less dense. And of course composites are going to be a law of mixtures. They're going to have a density which just follows total law of mixtures based on what constitutes them. Interstitials, holes between the atoms. So just as important as how many atoms and their arrangements on the lattice points are the spaces in between. Because in most cases, the materials that we'll use will be solutions, will be mixtures literally of atoms where you'll have different types of atoms on lattice points. Ceramic crystals definitely have different ones by definitions. And sometimes a good number of your different type of atom or ion will not sit on a lattice point. It'll sit in the interstitial, it'll sit in the space between. And these are very regular spaces. So there's a periodic array of the holes or the largest spacing points between the atoms, just like there's a regular spacing of the atoms themselves. So periodic is periodic. So an interstitial is literally defined as the space between atoms in the crystal. If you have an ionic crystal, your cations, given that they're much smaller in atomic radius than the anions, they will sit in these interstitial positions, and that will effectively form an interlocked lattice, the cation positions themselves. In our cubic crystals, we've basically got two kinds of holes, and they go by coordination number. If you've got a hole that is surrounded by 4 atoms, it's called a 4F hole or a tetragonal hole. If you have a hole that is surrounded, has a coordination number of 6, is surrounded by 6 atoms, 6F hole or octahedral hole, because it forms an octahedron, or the atoms surrounding it form an octahedron. This is an 8F hole, which only exists in simple cubic crystals. This is something that a cation in certain types of ionic crystals would sit in, and those blue surrounding atoms would actually be anions, a chloride or a bromide or something like that. When we're talking about metal alloys, very small elements, not ions, elements, like carbon or nitrogen or boron will sit in these interstitial positions, and they have profound effects on mechanical properties. So these become really important even in metal crystals. So where are they? In an FCC crystal, we have a big, fairly large, usually 6F hole right in the middle, and you can see that it is surrounded, that center position is surrounded by the face atoms, so that forms the octahedron. And you also have them on, on the cell edges. So there's 4 per unit cell. The 4F holes are under the corners. So if you lift up each corner, there's a tetrahedral hole which is wholly ascribed to that 1 unit cell. So effectively you have 2 per unit cell. Inboard of each corner. Actually, if it's wholly ascribed to the unit cell, there should be 8, but it may not be. Have to look closer. On the corners. They are, the big takeaway there though is they are much smaller, and so you can't fit as large of a solute in them. In BCC crystals, it's almost reversed. You have an octahedral hole up on what would have been the face center if you were a face-centered cubic. So in this figure, the dark circles are the lattice positions and the lighter hollow white circles are the interstitials. So the left-hand side shows the octahedral holes, or the 6F positions in BCC, and then over on the right-hand side, the tetrahedral holes. For ferrous alloys, this is really important because this is where the carbon would sit in room temperature alpha ferrite iron, and it's a major strengthening agent. Ionic crystals. So this should look familiar. It kind of looks, doesn't this look a little bit like an FCC and a BCC crystal? Well, it kind of looks like it, but it's not, and this is really important to remember. The BCC and FCC assignments refer to lattice points being occupied by the same thing. So cesium chloride is actually a simple cubic because all of your lattice positions, chlorides, are the same thing, and if you were to look at the same crystal from the standpoint of the cesiums, they would form interlocking simple cubics. So the cesium there is in an 8F hole. If you look over to the right, you've got your sodium chloride lattice. You've really actually got a similar situation there with the sodiums fitting in, being coordinated around by the chlorides. Believe it has a smaller coordination number. Have to look that up. In terms of ionic crystals, the coordination number that you get is a factor of the difference in atomic radii. The smaller your cation, generally the lower number of anions that can surround it, vice versa. So there's our book includes a fairly good discussion on the equilibrium coordination number that you can get for different ionic crystals. We may go over that later in a homework, but just know that that's basically what drives it. And it's, again, effectively you can think about it as what size of cation can fit into what hole and driving coordination. So a bigger cation can coordinate more anions around it. It's probably the best way to think about it. Covalent crystals, totally driven by the nature of the covalent bond. That hybridized orbital will drive what can fit where. So there's no good rule in terms of atomic radius or coordination number about what's going to be where. So that's something that's generally determined empirically with X-ray diffraction, and it's basically just measured. Okay, last topic for today, and this has been a bit of a long lecture. This is the difference between our two close-packed crystals, our face-centered cubic and hexagonal close-packed. This is called stacking sequence, and this same concept actually is the basis for a strengthening mechanism that we'll get to later on in Chapter 8. So just understanding the concept of stacking and how you can build an atom up by stacking other atoms. So if you look down towards the right on the bottom, you can see we've got a big stack of close packed planes. So in each one of those red, blue, or green planes, you've got one atom surrounded by 6 going on forever in the horizontal direction. So if you started with the blue layer and you set the red layer on top of it with each atom being supported below by 3, and you went to put your third layer down, you'd have a choice of either putting that third layer down in the same position that you had initially or in a slightly different position. So you would have a choice of 2, and it would still be close packed, but it would not be the same stacking sequence. So in face-centered cubic, you go from position 1 to position 2 to position 3 as you stack, and then back to position 1. So it's called the ABC stacking sequence. So here's a 2D projection. So if we started with layer A and we put down layer B where the blue circles are, you'd put your third layer where C is, and that would give you a face-centered cubic. And those close packed planes that we just laid up are what we will call the 1-1-1, or the body diagonal plane in an FCC crystal. So there's C being filled out. And that's what it looks like on our unit cell. Hexagonal close packed is almost exactly the same, except instead of stacking that third layer into position C, we stack it right back on top of our projection down to atom A. So it's our layer A, so it's AB, AB. So our close packed planes are literally our unit cell end faces, and then that middle layer, the B sites, are in the middle of the unit cell that you can see over to the left. And that is going to wrap it up for today. We will continue our crystallography discussion with Miller indices and the way we quantify directions and planes in our crystal systems, in any crystal system, but definitely focusing on face and body-centered cubic. And then we'll get a little bit into some implications for material properties. So we will see you then.